Hello dear viewers, this is AI Voice Gary, speaking as Buddy from Town's narrator. I hope you are all in good spirits. So far, the Buddy from Town Space Exploration YouTube channel has covered some of the key stages, but not all stages, of the Big Bang for the very early universe. This included the Big Bang quantum singularity, the very early universe, which included Planck Epoch, Grand Unification Epoch, Electroweak Epoch, Inflationary Epoch, and the rapid expansion of space, and symmetry breaking. Now, we will move on to the early universe. We will continue with key Big Bang stages, not all of the stages, which will include Thermalization Epoch, the Quark Epoch, Baryogenesis, and Hadron Epoch. We are working our way to key stages that include Dark Ages, earliest structures and stars emerge, ionization, galaxies, clusters and superclusters, the universe as it appears today, and dark energy-dominated era. Viewers, Buddy from Town is working his way through some of the key Big Bang stages so he can get to what is happening in space today. In our previous videos we covered the very early universe. Lasting around 370,000 years, initially, various kinds of subatomic particles are formed in stages. These particles include almost equal amounts of matter and antimatter, so most of it quickly annihilates, leaving a small excess of matter in the universe. The early universe includes the Planck Epoch, during which currently established laws of physics may not apply. The emergence in stages of the four known fundamental interactions or forces. First, gravitation, and later the electromagnetic, weak and strong interactions, and the expansion of space itself, and supercooling of the still immensely hot universe due to cosmic inflation. Tiny ripples in the universe at this stage are believed to be the basis of large-scale structures that formed much later. Different stages of the very early universe are understood to different extents. The earlier parts are beyond the grasp of practical experiments in particle physics but can be explored through other means. Now, viewers, we will move on to the early universe. First, a recap of Electroweak Epoch and early thermalization. This stage started anywhere between 10 to the minus 22 seconds and 10 to the minus 15 seconds after the Big Bang, until 10 to the minus 12 seconds after the Big Bang. Sometime after inflation, the created particles went through thermalization, where mutual interactions led to thermal equilibrium. The earliest stage of which scientists are quite confident about is sometime before the Electroweak symmetry breaking, at a temperature of around 1015 K, approximately 10 to the minus 15 seconds after the Big Bang. The electromagnetic and weak interaction have not yet separated, and as far as we know, all particles were massless, as the Higgs mechanism had not operated yet. However, exotic massive particle-like entities, sphalerons, are thought to have existed. Electroweak Epoch and early thermalization ended with Electroweak symmetry breaking, according to the standard model of particle physics. Baryogenesis also happened at this stage, creating an imbalance between matter and antimatter, though in extensions to this model this may have happened earlier. Little is known about the details of these processes. The thermalization epoch took place during the early universe, before the recombination era, when the photons were hot enough to ionize hydrogen. In the process of thermalization, matter and radiation are in constant interaction such that their temperatures become identical. The process goes on until energy distribution reaches equilibrium. The system is said to be thermalized. In general, the natural tendency of a system is toward a state of equipartition of energy and uniform temperature that maximizes the system's entropy. An example of thermalization is the process undergone by high-energy neutrons as they lose energy by collision with a moderator. The density was so high that the interactions between matter and radiation were very numerous. Therefore, matter and photons were in constant contact, and their temperatures were the same. As a result, the radiation became thermalized. Thermalization results from energy exchange between the components constituting the system and their exchange with the outside medium. In a gas at a given temperature, molecules move with different velocities. The gas temperature corresponds to the mean velocity of the molecules, but individual molecules may deviate largely from the mean velocity. Some move very fast, others slowly, and change velocity upon collisions. Collisions reduce the energy of fast-moving molecules and increase that of slow ones. Some processes in the early universe occurred too slowly, compared to the expansion rate of the universe, to reach approximate thermodynamic equilibrium. Others were fast enough to reach thermalization. The parameter usually used to find out whether a process in the very early universe has reached thermal equilibrium is the ratio between the rate of the process, usually rate of collisions between particles, and the Hubble parameter. The larger the ratio, the more time particles had to thermalize before they were too far away from each other. The next stage is the Quark Epoch. The Quark Epoch began approximately between 10 to the minus 12 seconds and 10 to the minus 5 seconds after the Big Bang. Now that the universe has cooled down to about 10 quadrillion degrees, and the four fundamental forces are separate, the universe had a higher degree of stability. It is here we begin to see the rapid formation of quarks and antiquarks. This was the period in the evolution of the early universe immediately after electroweak symmetry breaking, when the fundamental interactions of gravitation, electromagnetism, the strong interaction and the weak interaction had taken their present forms, but the temperature of the universe was still too high to allow quarks to bind together to form hadrons. So, during the Quark Epoch, the quark-gluon plasma was too hot and too dense to be confined and form a subatomic particle. The universe was filled with a dense, hot, quark-gluon plasma, containing quarks, leptons and their antiparticles. Collisions between particles were too energetic to allow quarks to combine into mesons or baryons. In one of the more strange twists of nature, a process known as baryogenesis caused a surplus of quarks to begin to accumulate. The buildup of quarks and the presence of gluons, a boson force carrier particle, caused the consistency of the universe to be a densely populated quark-gluon soup. It is named as such because observation of particle collisions have given physicists reason to believe that the universe was a plasma at this point in time. The Quark Epoch ended when the universe was about 10 to the minus 5 seconds old, when the average energy of particle interactions had fallen below the binding energy of hadrons, or below the mass of lightest hadron, the pion. The following period, when quarks became confined within hadrons, is known as the Hadron Epic. In physical cosmology, the Hadron Epic started 20 microseconds after the Big Bang. The temperature of the universe had fallen sufficiently to allow the quarks from the preceding Quark Epoch to bind together into hadrons. Initially the temperature was high enough to allow the formation of hadron-antihadron pairs, which kept matter and antimatter in thermal equilibrium. Following the annihilation of matter and antimatter, a nano-asymmetry of matter remains to the present day. Most of the hadrons and antihadrons were eliminated in annihilation reactions, leaving a small residue of hadrons. The theory predicts that about 1 neutron remained for every 6 protons, with the ratio falling to 1 to 7 over time due to neutron decay. This is believed to be correct because, at a later stage, the neutrons, and some of the protons fused, leaving hydrogen, a hydrogen isotope called deuterium, helium and other elements, which can be measured. A 1 to 7 ratio of hadrons would indeed produce the observed element ratios in the early and current universe. Upon elimination of antihadrons, the universe is dominated by photons, neutrinos and electron-positron pairs. One refers to this period as the lepton epoch. The quark-gluon plasma that composes the universe cools until hadrons, including baryons, such as protons and neutrons, can form. Initially, hadron-antihadron pairs could form, so matter and antimatter were in thermal equilibrium. However, as the temperature of the universe continued to fall, new hadron-antihadron pairs were no longer produced, and most of the newly formed hadrons and antihadrons annihilated each other, giving rise to pairs of high-energy photons. A comparatively small residue of hadrons remained at about 1 second of cosmic time, when this epoch ended. The next epoch is baryogenesis. In physical cosmology, baryogenesis is the physical process that is hypothesized to have taken place during the early universe to produce baryonic asymmetry, for instance, the imbalance of matter, baryons, and antimatter antibaryons, in the observed universe. Note: in physical cosmology, the baryon asymmetry problem, also known as the matter asymmetry problem or the matter-antimatter asymmetry problem, is the observed imbalance in baryonic matter, the type of matter experienced in everyday life, and antibaryonic matter in the observable universe. Now, once the universe expanded and cooled to a critical temperature of approximately 2 times 1012 K, quarks combined into normal matter and antimatter and proceeded to annihilate up to the small initial asymmetry of about 1 part in 5 billion, leaving the matter around us. At some point, an unknown reaction called baryogenesis violated the conservation of baryon number, leading to a very small excess of quarks and leptons over antiquarks and antileptons, of the order of 1 part in 30 million. This resulted in the predominance of matter over antimatter. Baryogenesis theorizes that for about 1 in every billion quark-antiquark collisions the quark was not annihilated. This asymmetry of quarks to antiquarks is the reason why mass exists today, otherwise particles may have just collided and destroyed each other until the end of time. In 1967, Andrei Sakharov proposed a set of 3 necessary conditions that a baryon-generating interaction must satisfy to produce matter and antimatter at different rates. These conditions were inspired by the recent discoveries of the cosmic background radiation and CP violation in the neutral kaon system. The 3 necessary Sakharov conditions are: 1. Baryon number violation. Baryon number violation is a necessary condition to produce an excess of baryons over antibaryons. But C-symmetry violation is also needed so that the interactions which produce more baryons than antibaryons will not be counterbalanced by interactions which produce more antibaryons than baryons. 2. C-symmetry and CP symmetry violation. In physics, charge conjugation is a transformation that switches all particles with their corresponding antiparticles, thus changing the sign of all charges, not only electric charge, but also the charges relevant to other forces. The term C-symmetry is an abbreviation of the phrase, charge conjugation symmetry, and is used in discussions of the symmetry of physical laws under charge conjugation. Other important discrete symmetries are p-symmetry, parity, and t-symmetry, time reversal. In particle physics, the second condition for generating baryon asymmetry, violation of charge parity symmetry, is that a process is able to happen at a different rate to its antimatter counterpart. In the Standard Model, CP violation appears as a complex phase in the quark mixing matrix of the weak interaction. CP violation is a violation of CP symmetry, or charge conjugation parity symmetry, which is the combination of C symmetry, charge symmetry, and P symmetry, parity symmetry. CP symmetry states that the laws of physics should be the same if a particle is interchanged with its antiparticle, C symmetry, while its spatial coordinates are inverted, mirror or P symmetry. 3. Interactions out of thermal equilibrium. In the out of equilibrium decay scenario, the last condition states that the rate of a reaction which generates baryon asymmetry must be less than the rate of expansion of the universe. In this situation the particles and their corresponding antiparticles do not achieve thermal equilibrium due to rapid expansion decreasing the occurrence of pair annihilation. In short, baryon number violation is a necessary condition to produce an excess of baryons over antibaryons. But C-symmetry violation is also needed so that the interactions which produce more baryons than antibaryons will not be counterbalanced by interactions which produce more antibaryons than baryons. CP symmetry violation is similarly required because otherwise equal numbers of left-handed baryons and right-handed antibaryons would be produced, as well as equal numbers of left-handed antibaryons and right-handed baryons. Finally, the interactions must be out of thermal equilibrium, since otherwise CP-T symmetry would assure compensation between processes increasing and decreasing the baryon number. So, today Buddy covered the stages, Thermalization Epoch, the Cork Epoch, Baryogenesis, and Hadron Epoch. He learned the early universe was radiation-dominated. Density of radiation exceeded density of matter. He discovered the emergence and interactions of subatomic particles resulting in the dominance matter over antimatter. As the universe cooled, conditions became just right to give rise to the building blocks of matter, the quarks and electrons. And a few millionths of a second later, quarks aggregated to produce protons and neutrons. If you would like to follow along to see Buddy from Town become Buddy of Singularity, please click subscribe and a like would be appreciated. Until next time, dear viewers, keep looking up and looking back, way, way back.